Good morning. We are talking about chapter 14 in this video. It's on waves, beaches, and coastlines, and the goal is to get us ready to do a lab on the different types of shorelines. So we'll start out refreshing what you know about waves. In deep ocean, a water wave is really not all that tall, 2 to 5 meters high, but they're usually fairly long and they move at anywhere from 30 to 90 kilometers per hour, so 15 to 45 or so miles per hour. When a wave moves, it's not an individual water molecule that picks up and skims along the surface, but instead it's the wave's energy that gets transported. So one water molecule bumps into the next water molecule, who bumps into the one next to it. So it's the energy that moves along, not the actual molecules themselves. You can think of people in a line. If somebody at the back of the line pushes, the push might go forward, but he is still at the back of the line. Okay, enough about waves. Let's look at beach structure. So beaches have some standard features to them. And here's a little graphic, and then we'll fill in the one below in just a second. So normally, if you've got a beach, the sediment is protected from the full force of the waves. Without that protection, the sand wouldn't accumulate. So you can see there's a low tide, and it'll come and make a mark on the beach, and there's a high tide, and it'll come and make a mark on the beach. And then there are some different locations. So we will look at this in the larger drawing found below, which is basically the same thing. So this line represents our low tide mark. It comes and makes a mark on the sand. This line represents our high tide mark. It comes and hits the sand. This part of the beach between high tide and low tide is called the foreshore. Between high tide and low tide, it's called the foreshore. And this is the sand that if you are at the beach, you could walk on it. It's hard packed. So when the tide is out, it's firm, and as the tide starts coming in, of course, it gets reduced. So the part that's from the high tide mark back landward is called the back shore. And that sand is never wet. It's always dry, and it's the sand that's really hard to walk on. And then finally, the sand that's always underwater is called the offshore. So we have back shore, it's always dry. Foreshore, it's wet at high tide, dry at low tide, kind of damp actually. And then offshore, the sand is always wet. So we've got our basic dividing lines based on where is the high tide, that's one mark, and where is the low tide, that's our second mark. And so those two marks divide our beach up into 3 sections. You can see in this diagram, we also have what look like sand dunes. So those are berms. The one that occurs farthest away from the water is called the winter berm. Winter storms tend to have larger waves and they push the sand back. And the one that's closest to the water is called the summer berm. So winter berm and summer berm. And again, a berm is just a sand dune, if you will. I know most of us have our experience with these at the beach, but you can have a berm in a desert as well. So let's talk a little bit about those tides. The tide is controlled primarily by the gravitational attraction of the moon and the sun for the water on the surface of the earth. And so the water on the surface of the earth is pulled towards the sun, it's pulled towards the moon. This water that's being pulled is called the tidal bulge. So it'll pull in the line that connects the earth with the moon, and then at 90 degrees to that, there's always less. So in this first drawing, if you could take your pencil and connect it with the moon and the earth, that's the line you would find your high tides on. And at 90 degrees to that, that would be where you'd find your low tides. Now, the Earth rotates on its axis once every 24 hours. So if you are right here and at a high tide, in 6 hours, you're going to be over here and be at a low tide. A total of 12 hours after you started, you'd get another high tide. And then 18 hours after you started, you'd get another low tide. And 24 hours, you'd be back at your high tide position. So roughly every 6 hours, not exactly, but approximately, you go from high to low to high to low and back to high again. Now the moon doesn't stay fixed. The moon actually changes its position. And so if we look at this diagram, we have the sunlight coming from the right-hand side in this particular picture, and here is the Earth. When the sun is on the back side of the moon, we say it's a new moon. And so if you were in a spaceship and you could fly around the moon and completely circle it, you'd be able to see the sunny side. But from Earth, we see the dark side. And so a new moon pretty much looks really dark. You might see a faint outline, but not very much. If you move into a crescent moon, and then finally we continue, because again, remember the moon moves around the Earth. The Earth rotates on its axis, but roughly every 28 days, the moon completes a cycle around the Earth. So if it starts here at the new moon, in roughly 7 days, it's going to be at the first quarter position. And so half of it's going to be light and the other half's going to be dark. At 7 more days, it's going to be way over here on the other side, and that is the full moon. So the sunlight hits the moon, and we now are on the bright side of the moon, and it'll look full. And then we come around to another 7 days from full moon to third quarter, and again, half the moon looks bright compared to when we started. You'll notice it's the opposite half from the first quarter. And then finally, at the end of that 28-day cycle, you're back at the new moon position. So the moon moves around the Earth and the Earth rotates on our axis. Okay. So spring tides are tides of maximum variation. That means the high tide is as high as it's going to get, the low tide is as low as it's going to get. And that happens at the new moon and the full moon, because that's when the moon and the sun line up with each other. And it's like a tug of war. They both pull on the water, and it results in a maximum high tide. So again, if you line up your pencil between, this is the Earth, you line up your pencil so that the Earth connects to the moon, that's the line the high tide falls on. And at 90 degrees to that, you'd have low tides. And again, this is an aerial view. We're looking down on top of it. So we're hovering in our magic spacecraft. In the full moon, you have the moon is on the opposite side from the sun. And so there's still a tug of war going on. And the moon pulls on the water and the sun pulls on the water. And again, if you line up your pencil with the moon and the Earth, that's the line the high tides fall on, and low tides would be at 90 degrees to that. Neap tides are tides of minimum variation. So that means that the high tide's not all that high and the low tide's not all that low. All right, high tide's not so high, low tide's not so low. And that's because the moon and the sun are at 90 degrees to each other. So that's that first quarter and third quarter position for our moons. And again, high tide, you find the moon, you line up your pencil with the Earth and the moon, and that's the line the high tides fall on. And at 90 degrees to that will be the low tide. And then third quarter, the moon's all the way down here. And again, line up your pencil. High tides fall on the line connecting the Earth and the moon. And low tides at 90 degrees to that. All right, let's talk about how the sand moves down the beach. So longshore drift of sediments, another way to talk about sand moving. It's another way to talk about sand moving. So the waves strike the beach at an angle and they're forced to move parallel. It forces the sand to move parallel. So you've got your wave. Waves don't ever come in just straight in and straight back. If you've ever gone to the beach, you've noticed these fan-shaped patterns in the sand as the wave washes onto the shore. So there's always this sort of up and over version of it. And that up and over does that to the sand. It brings the sand in, and then as the wave washes back out, it makes some of the sand move down. And the end result is that sand will migrate down the beach. If we could tag the sand somehow, we could put pink sand in, a bag of pink sand, you could watch it migrate down the shoreline. So let's look at our drawing. So the incoming wave is called the swash. The incoming wave, which is this sort of pinky arrow going to, is the swash. It curves in, again, makes those fan-shaped waves on the beach. The outgoing wave is the backwash, and it rolls straight back off. And the end result is that longshore drift is the pattern the sand makes as it kind of hopscotches down the beach. So when a wave strikes a coastline that has some sort of a change in it, so not a straight coastline, but one maybe that has a bay, so it dips down, or maybe there's a river coming into it, so that, again, there's an opening there. When the coastline goes from being straight to some sort of little notch in it, so that little notch means that the water experiences an abrupt change in direction, and you get some interesting land formations. One thing you would get could be a sand spit. So those are deposits which extend into the bay. So if here is our drawing, you ought to be able to do these drawings. So I've drawn, you don't have to shade it, or you can just do it with your pencil. So the part that sticks out into the bay is the sand spit. So this little finger of land sticking out into the bay is the sand spit, and the ocean is out here. The sand spit points in the direction that the current is moving. So ours is going, if north is at the top of the page, which it is in traditional maps, if north is at the top, so this sand spit is going from west to east, and that would tell us that the currents are moving from west to east. If you leave that sand spit undisturbed for a long period of time and there aren't any big storms, you might get a bay mouth bar. So if the sand spit just grows and grows and grows and completely isolates the bay, then you have what we call a bay mouth bar. So in a bay mouth bar, what used to be the bay is now a lagoon. A lagoon can be thought of as like a saltwater lake. It's full of salt water, but it doesn't have a direct inlet or outlet to the ocean. So it's isolated from the ocean. And again, we have our land, and this little strip between the lagoon and the ocean is the bay mouth bar. And again, you need to be able to draw these diagrams. Barrier islands are islands that cut across the opening of a bay. They form in a variety of ways. You could have a really long sand spit. Maybe our original sand spit went all the way out to here. And then a storm came and chopped it up into three pieces: the part that's attached to the mainland, the part that's the two, and then separated the remaining part into two little islands. Those islands are called barrier islands. And it could happen, maybe a sand spit wasn't in place. Maybe we had completely isolated the bay to make a lagoon, and we had a bay mouth bar. If that gets broken up into pieces, again, those pieces are now barrier islands. And I see I forgot to label this the land, but you do need to do that. I forgot to label it land, but you do need to do that. And so we will insert. I don't think I want it to be blue. There we go. Now I fixed it. All right, moving along. So suppose you don't want your bay to turn into a lagoon. Maybe you want to keep it open because you want access. Well, you're going to need a jetty. So jetties are rock walls that are built in pairs. You don't have a single jetty, you have pairs of them. And they're built to keep a bay open, to prevent sediment from closing off the bay. And so you have in this drawing, so it's a rock wall, this is the land, and these things that stick out are the jetties, and obviously this blue at the top of the drawing is the ocean. So the way we have it set up, it says the littoral drift is from west to east, so that means the sand would move that direction. If it weren't for the jetties, a sand spit and maybe a baymouth bar would extend from the left side of the drawing to the right. So with the jetty in place, the sand still moves from west to east, but it piles up against the jetty and it does not block the bay. And on the opposite side, sand is actually taken away. So you have a zone of accretion and a zone of erosion. Accretion is where the sand piles up. Erosion is where it is taken away. And over time, you can have some significant differences. So here you will see a photograph. I apologize, I don't know exactly where it is. I got it off a government website. I'll be honest, I have no idea what city it's in. It's awfully flat, but who knows. So you'll see here's the jetty going and the pair of jetties going out. And you'll notice that on the left side of the photograph, the beach is really deep. Here are the hotels and whatever. And on the right side, the beach is very narrow. So we know that the sand is moving from the left side of the photograph to the right side of the photograph. This is the zone of accretion, and this is the zone of erosion. And they did it to keep this bay open so you could have boats coming in and out of this harbor. All right, sometimes you don't need to keep the harbor open, but you want to keep the beach built up. And in that instance, you need groins. You can have one groin or two or 10. These are walls. They're short walls that are built out into the ocean. So they go from the beach into the ocean. And the whole idea is that they trap sand so that the beach doesn't become super skinny. They want to trap the sand and it only moves a short distance down. So in this drawing, we have our groins. That's what these walls are. Again, this is an overhead view. We're looking down on it. And if we know that the sand is going from west to east, so from left to right, then on the left side of each groin, sand will pile up, and on the right side, it's going to be taken away. Left side piled up, right side taken away. So you have, again, a zone of accretion and a zone of erosion, or updrift and downdrift. And here is a photograph. This is in Santa Monica, California. And you can see we have a series of groins. There's one here and here and here. And you will notice that on this photograph, on the sort of northeast side of the groin, so that would be right here, sand is piling up, but on the southern side of it, sand is being eaten away. So zone of accretion, zone of erosion. And you'll see that pattern on each of them. The side that's closest to the top of the photograph is where the sand piles up. The side that's closest to the bottom of the photograph is where sand is taken away. We're going to save our discussion of coast and coastal features for your lab. So you will want to look at it there.